Foreword. This manual is intended for engineers, designers, and scientists on the verge of a technological revolution. The imminent public disclosure of the principles behind generating and manipulating relativity fields will reshape every facet of our world. While the knowledge to create these fields remains restricted pending global regulatory frameworks, see Module 4 on ethical considerations, the time to prepare for their application is now. This document serves as a foundational guide to the three primary technological pillars that will arise from this new physics: radiant augmented gravity, RAG forging, gravity kiln crystallization, and transphasic material fusion, TMF. It is anticipated that these foundational technologies will be released as black box deployable units. This means that engineers and scientists will be provided with fully operational devices, essentially plug and play systems, without requiring them to delve into the complex physics or engineering of how the relativity fields themselves are generated. These units will feature sophisticated computer interfaces for controlling all relevant operational parameters, e.g., field strength, oscillation frequencies, processing times, pertinent to their intended function. Your focus, therefore, will be on the innovative application of these powerful tools. Our approach is progressive. Each section builds upon the last, taking you from refining raw materials to creating atomically perfect components, and finally, to fusing them into materials with properties previously thought impossible. We will root each new concept in the established academic principles you already know, demonstrating that relativity engineering is not magic, but a predictable extension of known physics. It should be acknowledged that the generation and precise control of the powerful relativity fields described herein are presumed to be significant engineering achievements, likely involving substantial energy resources, the specifics of which are beyond the current scope but are critical for practical implementation. So, yeah, welcome. We're going to be reading this document out of order. We're going to be reading Module 4 before the other three modules, and Module 4 is much closer to this channel. I guess just being digestible by normal people, but also kind of like the ethos of this channel. And modules 1 through 3 are more scientific in nature and deal more with the technology and the synthesis of the technologies involved with reverse engineering, UAP or UFO craft, and all the government secrecy programs. This is kind of the fruit of that with the whistleblower and disclosure stuff. But yeah, this is just for in case you're wondering why I'm reading this out of order. All right, so yeah, now that that's out of the way, let's get ready for Module 4: Ethical Imperatives and the Governance of Transformative Power. 1. The engineer's burden in an age of unprecedented capability. The preceding modules have delineated the extraordinary constructive potential of relativity engineering, offering glimpses of a future where humanity might overcome long-standing challenges of material scarcity, energy limitations, and environmental degradation. Technologies such as radiant augmented gravity, RAG forging, gravity kiln crystallization, and transphasic material fusion, TMF, promise paradigm shifts in material science and energy production, potentially reshaping civilization for the better. However, the history of scientific and technological advancement teaches a sobering lesson. Power of such magnitude is invariably a double-edged sword. As engineers and scientists, pragmatism dictates that we analyze not only the intended, beneficial applications of a technology, but also its potential for misuse, unintended consequences, and even deliberate weaponization. To ignore this dual-use nature, particularly with a technology as foundational as the manipulation of relativity fields, would be an act of profound negligence. This engineer's burden, as it might be termed, is not a responsibility unique to the pioneers of relativity engineering. It is a recurring theme that echoes through the annals of science and technology whenever transformative discoveries have been made. From the alchemists who sought the philosopher's stone, to the physicists who unlocked the atom, and the biologists who first spliced genes, the creators of potent new knowledge have consistently found themselves confronting ethical dilemmas that transcend purely technical considerations. The capacity to reshape the world carries with it an inherent responsibility for the potential consequences of that reshaping. Thus, the call to action within this manual is part of a larger historical narrative of scientific accountability. A critical component of discharging this responsibility is the careful consideration of historical precedent. Understanding how humanity has previously navigated the emergence of world altering technologies is not merely an academic exercise. It is a vital source of wisdom, offering insights into patterns of challenge, response, success, and failure. These historical echoes can inform our approach to the governance of relativity engineering, helping to anticipate pitfalls and identify strategies for fostering responsible development. The very notion that technology is entirely neutral, with its ethical valence determined solely by its application, is challenged by the scale of power inherent in relativity fields. While it is true that any tool can be misused, some technologies, by their intrinsic nature and the ease with which their destructive potential can be unleashed, demand a more profound level of scrutiny from their inception. The discussions surrounding the weaponization potential of TMF later in this module underscore this point. The development of nuclear weapons, for instance, was primarily driven by wartime imperatives for destructive power. Similarly, the advent of recombinant DNA technology immediately brought forth concerns about the accidental or deliberate creation of harmful biological agents. These examples illustrate that the potential for misuse is often deeply intertwined with a technology's core attributes. Specifically, RAG forging's capacity for precise isotope separation, Module 1, could be diverted for enriching fissile materials essential for nuclear weapons. Gravity Kiln crystallization, Module 2, by producing perfect single crystals with superior strength and electromagnetic properties, could enable the manufacture of advanced components for next generation weaponry, such as missile guidance systems or energy weapon components. Most alarmingly, transphasic material fusion, Module 3, with its potential to create materials of unprecedented density and strength from common elements, directly enables the conceptualization of novel, highly destructive weapons as detailed later. Consequently, the ethical challenge posed by relativity engineering is not confined to managing its applications. It extends to the governance of the development and dissemination of the fundamental knowledge and capability itself. This necessitates a more comprehensive and preemptive approach to oversight that has often been the case with past technological revolutions. 2. Echoes from the past, navigating the perils of dual-use technologies. The advent of relativity engineering, with its promise to reshape every facet of our world, places humanity at a familiar crossroads, albeit one with potentially higher stakes than ever before. To navigate this juncture wisely, it is instructive to examine how previous generations have contended with technologies that carried both immense promise and profound peril. Two historical episodes, in particular, offer crucial, albeit contrasting, lessons. The development of nuclear weapons, and the scientific community's response to the dawn of recombinant DNA technology. While each technological saga is unique in its specifics and context, common patterns of challenge, scientific response, social reaction, and regulatory evolution emerge, providing a valuable framework for considering the future of relativity engineering. A. The Nuclear Dawn and Its Long Shadow, a chronicle of delayed oversight. The journey to unlocking the power of the atom was a testament to scientific ingenuity, spanning decades of fundamental research in the early 20th century that gradually unveiled the secrets of nuclear fission. Discoveries by luminaries such as Rutherford, the Curies, Fermi, and Szilard laid the theoretical groundwork. However, it was the crucible of global conflict that transformed theoretical possibility into terrifying reality. The outbreak of World War II, coupled with the chilling prospect that Nazi Germany might develop an atomic weapon first, provided the critical impetus for the highly secretive, government-driven Manhattan Project in the United States. This wartime imperative dramatically accelerated the pace of technological development, often overshadowing broader ethical deliberations and considerations of long-term global control. The focus was, understandably, perhaps given the existential threat, on achieving a decisive military capability. The first physical manifestation of this new, almost unimaginable power occurred on July 16, 1945, with the Trinity test in the New Mexico desert. This successful detonation of a plutonium implosion device was a somber triumph, confirming the feasibility of an atomic bomb. Less than a month later, the world witnessed the devastating consequences of this technology. The atomic bombing of Hiroshima on August 6, 1945, followed by the bombing of Nagasaki on August 9, 1945, unleashed unprecedented destruction, instantly killing tens of thousands and ushering in the nuclear age. These events marked an irrevocable turning point in the history of warfare, international relations, and humanity's relationship with its own technological creations. The sheer destructive capacity demonstrated at Hiroshima and Nagasaki shocked the global conscience and precipitated a scramble for control. It became starkly apparent that a world armed with nuclear weapons was a fundamentally more dangerous place. The post-war era saw numerous proposals and complex negotiations aimed at establishing international oversight of atomic energy. However, these efforts were largely reactive, attempting to manage a technology that had already been weaponized and deployed, and whose secrets were beginning to proliferate. The establishment of the International Atomic Energy Agency, IAEA, in 1957, with a mandate to promote the peaceful uses of nuclear energy and to apply safeguards against its military diversion, was a significant step. Yet, the IAEA's effectiveness has always been contingent upon the cooperation of member states and constrained by the geopolitical realities of a world where several nations already possessed nuclear arsenals. A cornerstone of the non-proliferation regime, the Treaty on the Non-Proliferation of Nuclear Weapons, NPT, was signed in 1968 and entered into force in 1970. The NPT aimed to prevent the spread of nuclear weapons beyond the 5 states that already possessed them, while promoting disarmament by those nuclear weapon states and facilitating access to peaceful nuclear technology for non-nuclear weapon states. While the NPT has been a critical instrument in limiting proliferation, its very structure acknowledged the existing reality of a multipolar nuclear world, a direct consequence of the delay in establishing comprehensive controls before the technology became a strategic asset. The history of nuclear weapons offers several critical lessons for the governance of relativity engineering. Firstly, the development occurred largely in secrecy, driven by overriding national security imperatives, which meant that broader ethical and international control discussions lagged significantly behind the advancement of the technology itself. Secondly, The initial regulatory frameworks were fundamentally reactive. They were attempts to manage an already existing strategic reality, the existence of nuclear weapons and a burgeoning arms race between superpowers, rather than to preemptively shape the development path of the technology. This created an escalation trap. Once the technology was weaponized and had proliferated to even a few key states, regulatory efforts necessarily shifted from prevention to the far more complex and perilous task of managing an existing escalating threat. The NPT, for example, while vital, codified a world with nuclear powers rather than preventing such a world from emerging in the first place. The IAEA's role, crucial as it is, involves verifying declared stockpiles and activities, which is inherently about managing an existing landscape of nuclear materials and capabilities. Thirdly, the nuclear saga underscores the immense difficulty, if not impossibility, of achieving universal verifiable disarmaments once such a powerful genie is out of the bottle. Prioritization of national interests, particularly in the competitive and fearful atmosphere of the early Cold War, actively hindered open discussion and the establishment of collaborative international oversight mechanisms when they might have been most effective, before the technology became deeply entrenched in national security doctrines. This serves as a stark warning for relativity engineering, a technology that, according to this manual, promises to reshape every facet of our world, and thus carries implications far transcending any single nation's interests. A reactive approach to relativity fields, mirroring the nuclear path, could prove catastrophic. B. The Aslamar Consensus, a landmark in scientific self governance. In contrast to the largely government driven and secretive developments of nuclear weapons, the early days of genetic engineering offer a different model for how a scientific community can respond to the emergence of a powerful, potentially hazardous new technology. The breakthroughs in creating recombinant DNA, rDNA, in the early 1970s were revolutionary. Experiments such as Paul Berg's successful splicing of DNA from two different viruses in 1971 and the subsequent creation of the first true rDNA molecules in 1972 by Stanley Cohen, Herbert Boyer, and their colleagues opened up the unprecedented capability to combine genetic material from disparate species. This power to rewrite the blueprint of life was met with both excitement for its potential benefits in medicine and agriculture, and with immediate concern within the scientific community about its potential biohazards. Scientists like Robert Pollack voiced early anxieties about the unforeseen risks, particularly the possibility of creating novel pathogens or cancer causing agents. This burgeoning awareness and sense of responsibility culminated in a remarkable act of scientific self governance. In July 1974, a group of prominent molecular biologists, led by Paul Berg, published a letter, often referred to as the Berg Letter, in major scientific journals like Science and Nature. This letter called for the voluntary, temporary moratorium on certain types of rDNA experiments, specifically those involving the creation of antibiotic resistance and novel organisms or the introduction of toxin genes or viral DNA into common bacteria like E. coli. The signatories urged their colleagues worldwide to defer such research until the potential hazards be more thoroughly assessed and appropriate safeguards developed. This was a significant moment, leading scientists proactively signaling caution and calling for a pause in their own promising field of research. The moratorium set the stage for the Aslamar Conference on Recombinant DNA Molecules, held in February 1975 at the Aslamar Conference grounds in Pacific Grove, California. Approximately 140 leading researchers, along with a small number of lawyers and physicians, convened to discuss the risks and benefits of rDNA technology, to establish guidelines for conducting research safely, and to consider whether the voluntary moratorium should be lifted. The conference was characterized by intense debate and a concerted effort to classify experiments based on their perceived level of risk. The key outcomes of the Aslamar conference were an agreement that most rDNA research should proceed, but under strict safeguards, and the development of a framework for these safeguards. This framework included principles for both physical containment, e.g., specialized laboratory procedures and equipment, and biological containment, e.g., using genetically disabled host organisms and vectors that could not survive outside the lab. Experiments were categorized into low, moderate, and high risk levels, with corresponding containment measures prescribed for each. For instance, experiments involving DNA from pathogenic organisms or those producing toxins were deemed high risk and required the most stringent containment. The recommendations formulated at Aslamar had a profound influence on subsequent policy. They formed the basis for the National Institute of Health, NIH, guidelines for research involving recombinant DNA molecules, first published in June 1976. These guidelines established a formal regulatory framework for federally funded rDNA research in the United States. The NIH also established the Recombinant DNA Advisory Committee, RAC, to oversee and regularly update these guidelines as scientific knowledge evolved. The Aslamar experience demonstrates the significant potential for a scientific community to proactively identify emerging risks associated with its work and to initiate processes of self-regulation. It was a landmark example of scientists taking the lead and acknowledging potential hazards and collaboratively proposing solutions. This internal initiative was crucial in shaping a regulatory landscape that was, at least initially, more informed by scientific expertise and potentially more nuanced than if regulations had been imposed entirely from the outside in response to a public crisis. The containment philosophy that emerged from Aslamar, with its tiered approach to risk and corresponding safety measures, embodied a practical application of the precautionary principle, taking steps to prevent harm before it occurs, even in the face of some uncertainty. Furthermore, the Aslamar process was not static. The NIH guidelines and the role of the RAC evolved over time as scientific understanding of rDNA technology and its risks matured. Early fears about the ease with which dangerous organisms could be created and escape were, in some cases, found to be overstated as more was learned about the natural barriers to gene transfer and the effectiveness of biological containment strategies. This adaptability, allowing for the relaxation of restrictions where justified by new evidence, is a crucial feature of a sustainable regulatory system. However, it is also important to acknowledge the specific context of Aslamar. While the potential biohazards of rDNA were serious, the technology did not, at that early stage, present the same immediate and easily conceptualized potential for globally catastrophic weaponization as nuclear fission. The primary concerns were centered on accidental release and unforeseen ecological or health consequences, rather than the deliberate creation of WMDs by state or non-state actors. This difference in the perceived nature and scale of the threat may have made self-regulation more feasible and publicly acceptable than it might be for a technology with more obvious and direct weaponization pathways. Nevertheless, Aslamar established a vital precedent for scientific responsibility and proactive engagement in the governance of powerful new technologies, paving the way for broader public and governmental involvement in the oversight process. C. Distilling wisdom for relativity engineering, the imperative of foresight and preemption. A comparative analysis of the nuclear and Aslamar pathways reveals stark contrasts and offers profound lessons for the impending era of relativity engineering. The development of nuclear technology was largely reactive in its ethical and regulatory dimensions, driven by military imperatives in a shroud of governmental secrecy. The primary focus was national security, and its immense destructive power became undeniably apparent only after its use. Consequently, international regulations struggled to catch up with a technology already deployed and proliferating, aiming to manage an existing arms race rather than prevent it. The Aslamar experience with recombinant DNA, conversely, was characterized by proactive engagement from within the scientific community. Driven by concerns over biosafety, scientists initiated a relatively open dialogue, leading to self imposed moratoria and the collaborative development of safety guidelines. Regulation, in this instance, co evolved with the technology, at least in its early stages, and was less dominated by immediate catastrophic weaponization fears. Relativity engineering, and particularly the transphasic material fusion, TMF, detailed in this manual, appears to combine the most challenging aspects of both historical precedents. It projects a potential for democratized, catastrophic destructive power that could equal or even exceed that of nuclear weapons. Simultaneously, it involves a fundamental alteration of matter and energy that requires a deep scientific understanding, akin to the complexities of genetic engineering. The assertion in Module 4 that TMF could lead to the democratization of the power of a star, where the primary barrier to creating weapons of mass destruction is access to knowledge rather than industrial scale, suggests that the nuclear proliferation model, if applied to relativity fields, could unfold with even more dangerous speed and scope. This knowledge hazard is a critical distinction. Nuclear non-proliferation efforts have heavily focused on controlling access to fissile materials, like enriched uranium and plutonium, the complex industrial technologies required for their production. While the knowledge to design a nuclear weapon is also controlled, the material barrier has been a significant impediment to proliferation. Relativity fields, as envisioned, could allow the construction of weapons of absolute power from common materials once the how-to is understood. This shifts the fundamental challenge of oversight from material control to knowledge management. While Aslamar also dealt with a knowledge hazard, how to create rDNA, the immediate concern was the tangible biological entities created, a material, albeit living, hazard. For relativity fields, the raw ingredients for misuse are potentially ubiquitous, making preemptive control of the knowledge itself paramount until robust global safeguards are in place. The Aslamar model of proactive scientific engagement and self-regulation offers a valuable starting point. However, the sheer scale of the potential destructive power of relativity fields, as chillingly illustrated by the TMF fission projectile case study, indicates that scientist-led initiatives, while essential for initial risk assessment and ethical dialogue, must rapidly transition to robust global and verifiable governmental and international oversight. A purely self-regulatory approach would likely be insufficient to manage the profound security implications. Therefore, the core lesson for relativity engineering is that a purely reactive approach, like that which characterized much of the early nuclear age, would be unacceptably perilous, potentially leading to an uncontrollable proliferation of devastating capabilities. Conversely, an approach relying solely on scientific self-regulation, as in the initial phases of Aslamar, may not be adequate for a technology with such immediate and profound weaponization potential. A hybrid, preemptive model is essential, one that draws on the scientific community's foresight, as demonstrated at Aslamar, but quickly establishes a comprehensive international framework for governance, learning from the delayed and often fraught efforts to control nuclear arms. The critical window for establishing such an international consensus on regulation is before the technology is fully realized, before divergent national interests and capabilities solidify. The nuclear case starkly illustrates how achieving consensus on control becomes exponentially more difficult once multiple actors possess the technology and integrate it into their strategic doctrines. While Aslamar benefited from international scientific participation that eventually influenced global practices, relativity engineering, with its immediate and universal implications, demands a concerted effort to build a global regulatory consensus from the very outset. Delaying this consensus building drastically reduces the chances of effective global control and risks a future where humanity is perpetually struggling to manage an already unmanageable threat. The following table provides a comparative analysis to crystallize these points. Okay, so there's a few more of these tables, and yeah, I'm not gonna read them. Doesn't really make for good reading. The rest of this document, read out of order, doesn't really make for good reading either, honestly. But yeah, if you want to pause the screen and read this, I would recommend it. There's definitely some interesting stuff being said here. It just makes for horrible casting or reading out loud. So yeah, check it out. And I'm just gonna, if you want to look at it in more depth, I'm gonna keep scrolling. Don't be afraid to pause the video. This one's kind of long too. Oh my god. Okay. Hope you've got a good look at the table. Let's move on. 3. Relativity fields. The apex of power and the precipice of peril. The theoretical capabilities of relativity engineering, particularly transphasic material fusion, TMF, as outlined in Module 3 of this manual, represent a leap in power so profound that it risks making even the destructive potential of nuclear weapons seem constrained. The case study of the transphasic fission projectile serves not merely as a theoretical exercise, but as a stark illustration of how the principles of relativity engineering could be applied to create weaponry of almost unimaginable destructive capability from seemingly innocuous starting points. The scenario posits the creation of a projectile from TMF layered material, potentially inducing fissility and common elements or creating custom fissile isotopes, and fired from a TMF enhanced railgun. The manual theorizes that the extreme densities achievable through TMF layering, for instance, 14 TMF layers applied to a base material like aluminum, density 2.7 grams per centimeter cubed, could achieve a density of roughly 37,142 grams per centimeter cubed, would theoretically allow a critical mass of 52 kilograms of this hyperdense material to be contained within the volume of a standard 7.62 times 51 millimeter NATO rifle bullet, approximately 1.4 centimeters cubed. Such a projectile, designed with 2 or more subcritical pieces engineered to become supercritical upon impact, akin to a gun-type fission weapon design, would be small enough for infantry deployment. The delivery system, a TMF-enhanced railgun, further amplifies the threat. Current experimental railguns achieve muzzle velocities around Mach 7 to 9. By applying TMF and crystalline metal principles to enhance the railgun's power systems and structural integrity, the manual projects a tenfold increase in muzzle velocity, reaching approximately 30,000 meters per second, or Mach 88. Such hypersonic speeds would render the projectile nearly indefensible by current or foreseeable technologies. The destructive yield of such a TMF fission projectile is estimated at 884 kilotons of TNT equivalent, assuming the complete fission of the 52 kilogram fissile mass, based on 1 kilogram of uranium-235, yielding about 17 kilotons. This is nearly 60 times the yield of the atomic bomb detonated over Hiroshima. A single man-portable weapon would thus possess a destructive capacity far exceeding that of the early atomic bombs, which so dramatically altered the course of history. This chilling projection echoes the qualitative leap in destructive power represented by the first nuclear weapons, but with an added dimension of concern: accessibility. Nuclear weapons require highly enriched uranium or plutonium, the production of which demands vast industrial and financial resources, forming a significant barrier to proliferation. TMF weaponry, as theorized, could potentially be constructed from common materials once the foundational knowledge of relativity field generation and manipulation is disseminated. This drastically lowers the threshold of accessibility to weapons of mass destruction, shifting the primary barrier from the industrial capacity to mere possession of knowledge. The implications extend beyond projectiles. The manual extrapolates to a future where TMF powered, megawatt class laser turrets can be mounted on military vehicles, capable of instantaneously cutting through any known armor, neutralizing personnel and equipment silently from miles away. This would signify not merely an evolution in warfare, but its absolute endpoint, rendering concepts of cover, armor, and tactical positioning meaningless. Such capabilities would create profound strategic instability. The Cold War, for all its terror, eventually settled into a precarious stability based on mutually assured destruction, MAD, where no side could launch a nuclear attack without ensuring its own annihilation. Indefensible TMF weapons could dismantle this logic of deterrence, potentially tempting actors to pursue a decisive first strike capability or triggering a frantic arms race to acquire the technology or prevent others from doing so. The regulator's dilemma, presented later in this module, becomes even more acute under such conditions. The unique aspects of TMF, the potential use of common materials for WMDs, the unprecedented densities achievable, the creation of indefensible delivery systems, and the prospect of energy weapons that redefine tactical engagement, collectively paint a picture of a technology whose destructive potential could dwarf that of the nuclear age. The lessons learned from humanity's struggle to control nuclear weapons are therefore not just analogous, they are directly applicable and perhaps even understated given the democratized and amplified threat that uncontrolled relativity engineering could represent. 4. The unavoidable mandate: forging a global compact for the age of relativity fields. The convergence of relativity engineering's immense power, the dire warnings from the nuclear age, and the qualified successes of proactive governance seen in the Aslamar experience leads to an inescapable conclusion. The imperative for robust, preemptive regulation of relativity fields is absolute. The potential for this technology to democratize the power of a star means that the barrier to acquiring weapons of mass destruction would no longer be the immense industrial and financial undertaking of enriching uranium or producing plutonium. Instead, the barrier would simply be access to the knowledge of how to generate and manipulate relativity fields. Once this how-to is understood, any sufficiently resourced and motivated group, be it a nation state, a rogue faction, or a sophisticated terrorist organization, could theoretically construct weapons of absolute power from readily available materials. This potential fundamentally alters the calculus of global security. The loaded gun analogy, used in this manual to describe the premature release of such knowledge into a world unprepared for its consequences, is not hyperbole. It is a historically informed assessment grounded in the destructive realities of the 20th century and the chilling projections derived from the principles of relativity engineering itself. Do anything less than establish a global, verifiable, and robust regulatory framework before the knowledge of creating relativity fields becomes public or widespread would be to court global catastrophe on an unprecedented scale. The nature of relativity fields, particularly the TMF applications, necessitates a paradigm shift in how humanity approaches the governance of powerful dual use technologies. Traditional arms control and non proliferation efforts, such as those applied to nuclear weapons, have focused heavily on controlling access to specific fissile materials, e.g., highly enriched uranium, plutonium, and the complex technologies required for their production and weaponization. The Aslamar process, while dealing with knowledge, primarily focused on biosafety containment protocols for experiments and the organisms they produced. Relativity engineering, however, presents a more profound challenge. The primary proliferation risk stems from the dissemination of knowledge that can transform common materials into weapons of extraordinary power. This means that conventional approaches like export controls on specific materials, safeguards on declared facilities, or even laboratory safety protocols, while potentially forming components of a broader strategy, are insufficient in themselves to address the core risk. A new paradigm of governance is required, one that prioritizes the responsible stewardship and, where necessary, the stringent control of fundamental scientific knowledge and its critical enabling technologies. This intervention into the scientific process, the potential restriction of access to certain knowledge until universally agreed upon and enforceable mechanisms for safe application are in place, is more profound than previously attempted on a global scale for dual use technologies. It demands an unprecedented level of international cooperation, transcending typical national interests and sovereign concerns, and recognition of the shared existential threat, and, conversely, the shared potential for immense benefit if managed wisely. Without such a preemptive global compact, the development of relativity fields could easily devolve into a competitive race to the bottom. As modeled in the regulator's dilemma exercise, nations or other actors might be tempted to pursue unilateral advantage by secretly developing these capabilities, mirroring the dynamics of the early nuclear arms race. The alternative, and the only conscionable path forward, is a collective race to responsible stewardship. This requires establishing the rules of engagement, verification mechanisms, and an international oversight body before the technological race begins in earnest. The historical narrative of nuclear proliferation and the Aslamar Conference serve to illuminate these starkly different outcomes that can result from reactive versus proactive approaches. For relativity engineering, the choice is clear. Foresight and preemption are not merely advisable, they are essential for the survival and flourishing of human civilization. 5. Charting the course. Exercises in geopolitical prudence and ethical advocacy. The calculations and scenarios detailed previously in this module illustrate a technological paradigm shift so fundamental that it destabilizes all prior assumptions of national power and security. As the individuals who will understand this technology most intimately, engineers and scientists bear a unique and unavoidable responsibility to help guide policy and public understanding. The following exercises are designed to move beyond purely technical problem solving into the realm of strategic thinking, ethical advocacy, and proactive governance. The task is not merely to find a value for X, but to model and influence human behavior, prevent global catastrophe, drawing upon the historical lessons of past transformative technologies. Exercise 1. The Regulator's Dilemma. Game Theory Simulation. Objective. To use game theory to analyze the strategic choices nations will face with the advent of TMF technology, and to understand why the temptation of absolute power leads to absolute risk. Background. The classic prisoner's dilemma provides a robust model for the choices facing competing actors when trust is low and incentives for unilateral action are high. This model is not merely theoretical. Its dynamics were evident in the Cold War nuclear arms race, where the pursuit of national security through escalating arsenals led to a situation of perilous global insecurity. We will adapt this for the onset of TMF technology. Assume two major powers, Nation A and Nation B, have just acquired the knowledge to create TMF weapons. They must each decide in secret whether to cooperate, pursue a verifiable global treaty to ban TMF weapons and share the technology for peaceful energy/material use only, or defect, secretly develop a TMF arsenal to achieve military supremacy. The payoff matrix. In the situation where both Nation A and Nation B cooperate, mutual prosperity. Both nations benefit from peaceful TMF tech, global stability. In the situation where Nation A cooperates and Nation B defects, annihilation/subjugation. Nation B achieves absolute power, Nation A is defenseless. Same thing for Nation A defecting and Nation B cooperating. If both nations defect, MAD, mutually assured destruction. Both nations possess absolute weapons. Any conflict, intentional or accidental, ensures total global annihilation. Tasks. For 1. Initial analysis. From a purely nationalistic and short-sighted perspective, what is the rational choice for Nation A if its sole goal is to win and it does not trust Nation B? Explain your reasoning based on the payoffs. 2. Risk reevaluation. Now, factor in the case study of the 884 kiloton TMF bullet. The outcome of negative infinity is not a strategic loss. It is the extinction of both nations and potentially all human life. Consider the historical reality of nuclear near misses during the Cold War, e.g., the Cuban Missile Crisis, and the ongoing burden of managing nuclear arsenals. How does this reframe the risk associated with the defect strategy? 3. The proliferation problem. Failure mode analysis. This model only assumes 2 actors. Now, expand the model to include 10 nation-states and 1 well-funded non-state terrorist group. Calculate the number of unique pairings of actors, potential conflicts. Qualitatively describe how the probability of an intentional or accidental launch leading to the negative infinity outcome changes as the number of actors with TMF weapons increases. Identify the single most likely failure mode that would lead to catastrophe in this multipolar scenario, e.g. miscalculation, state collapse, extremist ideology, technical malfunction, unauthorized use. 4. Policy brief. You are tasked with advising the leader of Nation A. Write a 1-page policy brief titled The Illusion of TMF Supremacy. Using your analysis and drawing parallels to the lessons from the nuclear arms race, argue why, despite the allure of the plus 1,000 payoff, the only rational and survivable strategy is to vigorously pursue cooperation and a verifiable treaty before widespread capability emerges. Your brief must translate the concept of infinite risk into a compelling political argument. Exercise 2. From the lab to leadership. Stakeholder communication strategy. Objective. To practice translating complex technical realities and their historical precedents into persuasive arguments for different non-technical audiences. Effective communication is a primary tool an engineer or scientist possesses to influence policy and foster responsible innovation. The Aslamar Conference, initiated by scientists, demonstrates the power of the expert community in shaping the dialogue around emerging technologies. Scenario. You've been asked to make the case for immediate international regulation of relativity fields to 3 critical stakeholders. For each stakeholder, Prepare a concise 5 bullet points maximum presentation outline and name one key visual aid you would use. Your argument should be informed by the technical capabilities of relativity fields, the weaponization scenarios, and the historical lessons from the nuclear age and the Aslamar process. Audience 1: A council of senior military generals. Their mindset: focused on national security, strategic advantage, deterrence, and threat assessment. They see weapons as tools to maintain peace through strength. Your task: convince them that this tool breaks the entire concept of strategy as currently understood, potentially rendering existing doctrines and defenses obsolete, much like nuclear weapons redefined warfare, with even lower barriers to proliferation of ultimate destructive power. Outline example: relativity field weapons, RFWs, unprecedented destructive power, reference 884 kiloton bullet versus Hiroshima. TMF railguns, near indefensible delivery, Mach 88, negating traditional missile defense. TMF energy weapons, instantaneous armor penetration, rendering current platforms vulnerable. Strategic instability, erodes deterrence, risk of use them or lose them mentality, end of conventional warfare. Historical parallel, nuclear weapons created MAD. RFWs could create universal vulnerability without stable deterrence. Preemptive global control is the only path to national and international security. Key visual aid, a comparative graphic showing the destructive radius and accessibility, materials, knowledge of a TMF projectile versus a conventional high explosive, a tactical nuclear weapon, and a strategic nuclear weapon. Audience 2: a committee of economic advisors and finance ministers. Their mindset: focused on GDP, economic stability, return on investment, and national prosperity. They may see TMF technology as a massive economic opportunity. Your task: convince them that the immense economic upside of peaceful applications, e.g., limitless energy, new materials, is entirely dependent on preventing the catastrophic downside of weaponization and proliferation. Outline example: peaceful TMF applications, unprecedented economic revolution, energy, materials, manufacturing. The cost of inaction: uncontrolled proliferation leads to global instability, arms races, and potential conflict. Economic impact of conflict far outweighs any short-term gains from unregulated development, compared to World War II economic devastation, but scaled up. Investment in security: robust international regulation and verification is an essential investment to secure the conditions for economic benefit. Historical lesson: Aslamar. Proactive safety and ethical guidelines in biotech fostered public trust and allowed a new industry to flourish. A similar approach is needed for TMF, but with global governmental authority. Key visual aid: split chart. One side showing projected global GDP growth and societal benefits with peaceful, regulated TMF, the other showing projected economic collapse and resource diversion in a TMF arms race scenario. Audience 3: the general public, via a televised interview. Their mindset: concerned with the safety of their families, their future, and fundamental fairness. They are susceptible to both fear and hope, and have a limited technical vocabulary. Your task: build a broad public consensus for stringent international regulation, empowering them to pressure their political leaders. The narrative must be clear, honest, and compelling. Outline example: a new power. Relativity fields offer amazing possibilities for a better future, clean energy, new medicines, solutions to big problems. A serious responsibility. This power, like atomic energy, can also be incredibly dangerous if it falls into the wrong hands or is misused. Learning from history. We learned with nuclear weapons that waiting too long to control them makes everyone less safe. We also learned from early DNA science that scientists and governments can work together to set safety rules before problems arise. The path to safety. We need strong international agreements and oversight now, before this technology is widely available, to ensure it's only used for good. Your voice matters. Public demand for responsible action can ensure our leaders make the right choices for a safe future with this powerful new science. Key visual aid. A simple animation depicting a switch that can direct the power of relativity fields towards global benefit, showing positive icons like clean energy, advanced medicine, or global risk, showing stark warning symbols, with the hand of international cooperation and oversight firmly on the switch, guiding it towards benefit. By engaging in such exercises, the engineering and scientific community can move beyond being mere creators of technology to becoming crucial architects of its responsible integration into society. The lessons of the past, both cautionary and inspiring, provide an indispensable compass for navigating the profound ethical and geopolitical challenges posed by the dawn of relativity engineering. The burden is heavy, but foresight, courage, and a commitment to global cooperation can chart a course towards a future where this unprecedented power serves humanity as a whole. Yeah, so, wow. This was originally the end of the document, but we're going to do things actually even weirder. I talked about how we read, the last module in this manual first. So next we're actually going to read module 3 before modules 1 or 2. I just think it's probably the most interesting way to put this video together. It is kind of a boring technical manual, but with very, very profound implications. So yeah, we're gonna go from module 4 to module 3, and then we'll go back to modules 1 and 2. Module 3. Transphasic Material Fusion, TMF, Unifying Matter Beyond Conventional Limits. Having achieved ultra-pure materials with RAG forging and perfect atomic structures with gravity kiln crystallization, the next frontier in relativity engineering is the fundamental recombination of matter in ways previously thought impossible. Conventional materials science combines elements through alloying, atomic mixtures, or macroscopic compositing. However, these methods have inherent limitations in terms of achievable properties and interface stability. This module introduces transphasic material fusion, TMF, the pinnacle of the currently understood relativity engineering applications. TMF utilizes class 3 transphasic fields to fuse two or more separate objects into a single unified whole by enabling the co-location and interpenetration of their atomic structures, creating materials with emergent properties far beyond those of their constituents or conventional combinations. Academic foundation. Beyond alloys and composites. Current material science combines materials in two primary ways. Alloys, a mixture on the atomic level, creating a new polycrystalline material with average properties, e.g. steel, brass. Composites, a macroscopic combination of distinct materials, e.g. carbon fiber, reinforced polymer. Their properties are excellent, but they are subject to delamination and interface failures. TMF transcends both. It is not a mixture or a layering, but a co-location of atomic structures. It can be thought of as the ultimate functionality graded material or metamaterial, where the properties are designed not by composition, but by the direct interpenetrating fusion of matter lattices. The precise quantum mechanical description of how distinct atomic lattices interpenetrate and maintain stability in a TMF fused state is a complex area of ongoing theoretical development. To further contextualize the profound material reconfigurations proposed by TMF, it is useful to consider other exotic states of matter predicted and explored within quantum mechanics. One such example is the supersolid state. A supersolid is a counterintuitive phase of matter that simultaneously exhibits the rigid crystalline order of a solid and the frictionless flow characteristic of a superfluid. This remarkable behavior, where atoms arrange into a stable lattice yet can also move through it without resistance, arises from quantum effects at extremely low temperatures and has been the subject of intense theoretical and experimental investigation for decades, with recent experiments providing evidence for its existence. While the underlying physics and formation mechanisms of supersolids, often involving Bose-Einstein condensates and specific interatomic interactions, are distinct from the proposed transphasic field manipulations of TMF, the verified existence and ongoing study of supersolids serves as a compelling illustration that quantum mechanics permits material states far beyond classical understanding. This landscape of established quantum phenomena, where matter behaves in highly non-classical ways, provides a supportive theoretical context for exploring the novel material configurations and properties, such as interpenetrating lattices envisioned by transphasic material fusion. Core principle of TMF: phase shift. Component is passed through a transphasic field armature, causing it to shift out of normal spacetime. Spatial collocation. Second component is moved into the exact physical space occupied by the first. Fusion. The transphasic field is disengaged, causing the first component to phase back in, using its atomic structure directly with the second. Primary design applications. Indestructible components. A TMF object of two identical materials has double the matter in the same volume, creating unprecedented strength. A key assumed characteristic of TMF-fused materials is their exceptional stability and integrity, even under extreme conditions or perpetual eternal stresses, such as those envisioned in the piezoelectric power cell. TMF-driven enhancements in magnets and generator design, towards ultimate energy conversion efficiency. Fusing a crystalline magnet with itself using TMF will theoretically lead to a substantial increase in the strength of the magnetic exchange interaction, far surpassing the gains from crystallization alone. Precise scaling of this magnetic enhancement requires further detailed investigation, but the potential for creating magnetic fields of unparalleled strength is a key research direction. This capability, when systematically applied to all critical components of an energy generation system, e.g. an electric flywheel generator, allows for a recontextualization of conventionally understood thermodynamic limits. Consider the factors determining generator output and efficiency: magnetic field density, the magnetic responsiveness and conductivity of stator windings, the number and packing density of these windings, the air gap between a rotor and stator, and frictional losses. TMF enhanced materials offer radical improvements in each area. Magnetic field density. TMF layering can create magnets with significantly higher field strengths. Conductor properties. TMF can produce conductors with superior magnetic responsiveness and conductivity, potentially using thinner wires due to enhanced material strength, thus allowing more windings in a given volume. Precision engineering. TMF manufacturing could enable virtually non-existent air gaps between rotor and stator, minimizing magnetic reluctance and excitation losses. Friction elimination. TMF-derived supermagnets can enable robust magnetic suspension of rotors, virtually eliminating mechanical friction. Enhanced transmissions. Magnetic transmissions built with TMF materials could offer near lossless power transfer. While conventional generators have achieved high efficiencies, e.g. greater than 97%, they are still bound by the limitations of existing materials and manufacturing precision. The synergistic and simultaneous optimization of all these factors through TMF and relativity engineering principles could lead to energy generation systems whose useful output, relative to conventional input expectations, dramatically exceeds what was previously thought possible. This isn't about violating fundamental conservation laws by creating energy from nothing, but rather about so profoundly minimizing losses and optimizing energy conversion pathways. The established rules of thermodynamics, as applied to systems built with standard materials and forces, becomes a specific limited case. The history of science shows that physical laws, often perceived as absolute, can be revealed as specific cases or approximations when new physical regimes or interactions are discovered. For instance, Newtonian mechanics was shown by Einstein's theories of relativity to be an excellent approximation for everyday speeds and masses, but not universally applicable. Similarly, the caloric theory of heat was superseded by the mechanical theory of heat, and classical mechanics gave way to quantum mechanics at atomic scales. In this context, relativity engineering, through TMF, may demonstrate that the perceived limits of energy conversion efficiency are a function of our current material and engineering paradigm, not an immutable universal constant. The exploration of these TMF enabled ultra efficient energy systems is a critical research frontier. The forever battery. By leveraging piezoelectricity, TMF can create a permanent power source. Series 1. Conceptual design and theoretical application challenges. Exercise 3.1. The piezoelectric power cell. Scenario. Design a permanent microscopic power source for self-powered nanotechnology. Task. Select two crystalline materials with widely different coefficients of thermal expansion, e.g. a tungsten derivative and an aluminum derivative, but charge properties differentials conductive piezoelectric reaction if they were to be married in one material. Outline the TMF manufacturing process where one crystal is superheated and the other is supercooled at the moment of fusion. Explain the resulting physical state. Known piezoelectric materials like quartz or lead, zirconate titanate, PZT, generate voltage when their crystal lattice is mechanically strained. Describe how your TMF process induces a permanent maximum level internal strain by fusing one expanded lattice and one contracted lattice into a single perpetually stressed structure. Theorize how the resulting constant voltage could be used to power a nanite. Contrast this with conventional batteries, explaining why the TMF cell would not degrade. Exercise 3.2. Iterative TMF, gravity kiln, and RAG technology enhancement. Prompt. Utilizing the application principles in this module, transphasic material fusion, and the preceding modules, gravity kiln crystallization, RAG forging, provide detailed examples of how TMF enhanced materials can revolutionize these foundational technologies. Specifically, discuss how TMF fused components, e.g. materials with double density and unprecedented strength, or functionally graded materials with tailored properties, could be used to construct next-generation RAG forges, capable of generating and containing significantly higher G-forces, leading to even finer material purification and isotope separation. How TMF could be applied to create gravity kilns with superior thermal and pressure resistance, more stable and powerful ROG/RIG field emitters, or enhanced structural integrity, allowing for the synthesis of larger or more exotic single crystals under more extreme processing conditions. How TMF-derived materials might improve the TMF armature itself, perhaps leading to more efficient phase shifting, greater precision in spatial co-location, or the ability to fuse larger or more complex components. Series 2. Empirical protocol and metric development exercises. Preamble. Transphasic material fusion technology proposes the direct interpenetrating fusion of atomic structures, potentially leading to materials with properties that defy conventional expectations, such as doubled matter density within the same volume and exponentially enhanced magnetism. The subsequent research objective is to design an experimental framework capable of validating the fundamental claims of TMF and quantifying the performance of its most transformative and potentially paradigm shifting applications. For this exercise, assume access to TMF process samples and a suite of highly advanced, possibly bespoke, characterization capabilities necessary to probe these unprecedented material states. Exercise 3.3. Validating TMF integrity and quantifying novel phenomena. 1. Methods for assessing atomic level fusion, material homogeneity. The central claim of TMF is that it results in not a mixture or a layering, but a co-location of atomic structures. Verifying this assertion at the atomic scale is the foremost experimental challenge. It requires distinguishing true TMF from extremely fine-grained composites or intimately mixed alloys. Task. Propose experimental methods to confirm that TMF achieves a true interpenetration of matter lattices. What specific signatures at the atomic or near atomic scale would differentiate a TMF material from a conventional alloy or a nanoscale composite? Consider the required resolution and analytical capabilities of techniques such as aberration-corrected scanning transmission electron microscopy, STEM, coupled with electron energy loss spectroscopy, EELS, or energy dispersive X-ray spectroscopy, or chemical mapping at atomic resolution. Could atom probe tomography, which provides 3D atomic scale chemical imaging, be employed to verify the interpenetration of different atomic species if dissimilar materials were fused? Assess the homogeneity of a TMF component. If two different materials were fused, how would the interface, which in TMF theory is not a boundary but a region of co-location, be characterized? If a material is fused with itself, how would the uniformity of the doubled matter be assessed throughout the volume? Define quantitative metrics for a successful fusion at the atomic level. This might include parameters like the continuity of crystalographic planes across the fusion zone, if applicable, the absence of nanoscale voids or phase segregation that would indicate incomplete fusion, or statistical measures of atomic distribution. TMF posits material states, such as two distinct atoms effectively sharing the same spatial coordinates through interpenetrating lattices, that fundamentally challenge conventional material science. Characterizing such exotic states may require pushing the existing limits of analytical techniques or even conceptualizing entirely new measurement modalities. This exercise encourages students to think about how current cutting-edge tools designed for known material structures could be adapted or their data reinterpreted to provide evidence for or against the TMF hypothesis. It is a lesson in the co-evolution of material synthesis and metrology. New materials often demand new ways of seeing and measuring. The challenge lies in defining what observable evidence would uniquely support the TMF model over more conventional interpenetrations of material structure. 2. Experimental measurement of enhanced density and strength in TMF components. One of the most striking claims for TMF is that fusing an object with an identical copy results in double the matter in the same volume, creating unprecedented strength. Task. Design experiments to precisely measure the density of TMF components. Compare these measurements to the theoretical double density, i.e. twice the density of the original, unfused material. What are the significant challenges and potential sources of error in accurately determining both mass and, crucially, true volume for such objects, especially if their external dimensions do not change, but their mass doubles? Quantify the unprecedented strength of TMF materials. This involves standard mechanical testing procedures, e.g., tensile strength, compressive strength, fracture toughness, hardness, impact resistance, but applied to materials whose fundamental nature is novel. How would these properties compare not only to the base materials, but also to other state of the art advanced structural materials? Investigate the failure mechanisms of TMF materials under extreme stress. Do they exhibit novel fracture modes or deformation behaviors attributable to their unique interpenetrating atomic structures? Consider what non destructive testing (NDT) techniques could be adapted or developed for quality control and internal integrity assessment of TMF parts. Advanced ultrasonic methods like phased array ultrasonic testing (PAUT) or time of flight diffraction (TOFD) detect internal anomalies related to incomplete fusion or stress concentrations. Given the potential for extreme density, with techniques like terahertz imaging, which can probe dielectric material interiors, find any, perhaps hypothetical, applicability in assessing structural uniformity or detecting subsurface defects in non-metallic TMF constructs. 3. Research protocols for verifying enhanced magnetic properties and energy conversion claims. The manual states, using a crystalline magnet with itself will theoretically lead to a substantial increase in the strength of the magnetic exchange interaction. This capability allows for a recontextualization of conventionally understood thermodynamic limits in energy generation systems. This implies the potential for ultra-high efficiency energy conversion. Task: develop a research protocol to measure the fundamental magnetic properties of a TMF-enhanced magnet, e.g., a crystalline magnet fused with itself. This includes quantifying its magnetic field strength, B field and H field distribution, total magnetic energy stored, saturation magnetization, remanence, and coercivity. Design a rigorous experiment to test the energy conversion efficiency of a generator employing TMF-enhanced magnets and conductors. What are all the critical input and output energy forms and parameters that must be meticulously measured? For an electrical generator, this typically involves precise measurement of mechanical input power, torque and speed, often using a dynamometer, and electrical output power, voltage, current, power factor. How would all energy losses be comprehensively accounted for to validate claims of exceptionally high efficiency? These include frictional losses, even with magnetic bearings, thermal losses, Joule heating in windings, core losses, electromagnetic radiation, and any energy consumed by the TMF system itself if it requires active fields for component stability. Standard generator efficiency calculations often involve accounting for various segregated losses, bearing, windage, copper, iron losses, or using calorimetric methods to sum total heat dissipation. What specific metrics and criteria would definitively establish an efficiency that recontextualizes thermodynamic limits, e.g., an electrical power output that, after accounting for all inputs and losses, approaches or implies a near perfect conversion of input energy, challenging conventional loss models? What control experiments, calibration procedures, independent verification steps, and statistical analysis would be essential to ensure the credibility of such a result given its profound implications? The assertion of energy conversion efficiencies that push beyond conventionally understood limits, even if not violating fundamental conservation laws, demands an exceptionally high burden of proof. Any experimental design aimed at verifying such phenomena must be characterized by extreme rigor, meticulous attention to detail, and a proactive approach to identifying and eliminating all potential sources of error, bias, or misinterpretation. Students undertaking this part of the exercise must be challenged to think like skeptical scientists, anticipating criticisms and designing their protocol to be as unassailable as possible. This involves not only precise measurement of intended inputs and outputs, but also comprehensive qualification of all conceivable energy pathways and loss mechanisms. 4. Comprehensive test regimen for forever battery, performance, and longevity. The TMF Forever battery is theorized to generate a permanent voltage via piezoelectricity, arising from a perpetually stressed structure created by fusing two crystalline materials with widely different thermal expansion coefficients, one superheated and the other supercooled at the moment of fusion. The key claim is that it would not degrade. Piezoelectricity itself is a well-known phenomena where mechanical strain induces an electric field, and vice versa, in materials lacking a center of symmetry. Task: design a comprehensive testing regime for the TMF Forever battery. How would its key electrical output characteristics be measured? These include open circuit voltage, short circuit current, current capacity under various loads, internal resistance, power density, and energy density. The central claim is perpetual power and no degradation. How can such a claim be tested within a realistic experimental timeframe? While true perpetuity is untestable, proxies for extreme longevity must be developed. Consider adapting principles from accelerated aging tests used for conventional batteries or long-life electronic components, although the degradation mechanisms, or lack thereof, in a TMF battery would be fundamentally different. Could continuous high-resolution monitoring of output under constant load for extended periods reveal minute changes? What specific metrics would define no degradation, or an acceptably low level of degradation, consistent with forever in practical terms, e.g. less than X% change in voltage output or current delivery capability over Y simulated years, or equivalent operational cycles? How would the underlying piezoelectric mechanism be investigated? What experiments could confirm that the voltage is indeed generated by sustained internal strain in the fused lattice? How would the stability of this perpetually stressed structure be assessed under various operational conditions, such as temperature fluctuations, mechanical vibrations, or varying electrical loads? 5. Metrics for TMF process efficiency and control. Beyond the properties of TMF-derived materials, the TMF manufacturing process itself, phase shift, spatial collocation, fusion, needs to be characterized for efficiency, reliability, and controllability. Task: propose metrics to evaluate the TMF process. Consider fusion success rate, the percentage of attempted fusion operations that result in a successfully fused component meeting predefined quality criteria, e.g. achieving target density, strength, and structural integrity. Energy consumption: the total energy required per successful fusion event, or per unit volume/mass of TMF material created. This is crucial for assessing the economic and environmental viability of the process. Cycle time: the total time taken for a complete TMF operation on a given component or set of components. Precision of spatial collocation: the accuracy and repeatability with which the components can be aligned in the phase-shifted state before fusion. What are the acceptable tolerances, and how would this alignment be measured or verified, possibly in situ? What types of in-process monitoring, e.g. sensors for field strength and uniformity in the transphasic armature, systems for verifying component position during co-location, could provide data for these metrics and enable process control and optimization? And here is table 3. We're going to do the same thing for every table throughout this manual. So if you want to look at it, feel free to pause the screen while I scroll through it slowly. We've done things kind of weird so far. We looked at module 4, and then we looked at module 3. We're actually going to go back to module 1, and maybe the way we should have done it, but I think this is just the most interesting way to put the video together, And again, the entire manual is going to be linked in the comments, not the comments, the description. So yeah, check that out if you want to. But moving on to the next module. Module 1, Radiant Augmented Gravity, RAG Forging, Mastering Material Purity. The quest for materials with superior performance is often fundamentally limited by impurities. Even trace contaminants at the parts per billion level can degrade mechanical strength, alter electromagnetic properties, or reduce the efficiency of chemical and nuclear processes. This module introduces radiant augmented gravity, RAG, forging, a revolutionary technology designed to address this foundational challenge by achieving unprecedented levels of material purification. It explores the application of Class 1 radiant Type 1 augmented gravity fields, which allow for the precise generation of intense, localized gravitational fields, enabling unparalleled control over mass and matter separation. The ultra-high purity outputs from RAG forging are not merely end products. They serve as the ideal, often essential feedstock for the subsequent precision work of gravity kiln crystallization, Module 2, and the advanced atomic level bonding of transphasic material fusion, Module 3, where initial material quality dictates the ultimate performance of the final engineered systems. Academic Foundation, Centrifugal and High Gravity Metallurgy. The principle of using increased gravitational force to refine materials is well established in metallurgy. Centrifugal casting, a process in use for decades, employs rotational motion to create forces many times that of Earth's gravity. Studies published in journals like Metallurgical and Materials Transactions have extensively documented how, under high G conditions, molten alloys segregate based on density. Denser phases and impurities are forced to the outer radius, while lighter elements and dross collect at the inner radius. This technique is used to reduce porosity and refine the microstructure of cast components. RAG technology represents a paradigm shift beyond this principle. It provides gravitational forces orders of magnitudes greater than any mechanical centrifuge can achieve. Centrifuges can reach forces up to 100 times Earth's gravity, without introducing the rotational stresses, geometric constraints, or vibrations inherent to those systems. RAG systems are designed to generate effective gravitational accelerations in the range of 1000 Jeff to 10,000 Jeff or higher, offering a significant advantage over conventional centrifuges. They also offer pure, directional, and tunable gravity. Core principles of RAG application. Hypergravity filtration zone. Applying a strong downward vectored RAG field within a conduit forces particulate matter to settle out of a fluid, gas, or liquid stream at an accelerated rate, analogous to the sedimentation described by Stokes' law, but amplified to an extreme degree. Mass discrimination. The effect of a RAG field is proportional to the mass of the particles it influences. Heavier particles and isotopes, e.g., uranium, lead, are affected more strongly than lighter ones, allowing for precise, layered separation. Oscillating field enhancement. A simple constant increase in gravity, a DC equivalent, is effective. However, introducing a fluctuating or oscillating wave to the RAG field, an AC on DC equivalent, dramatically improves refinement. These gravitational tides travel through the material, agitating particles and accelerating the settling of heavy elements and the rise of lighter impurities. The optimal oscillation frequency, F, is tuned to the material being processed. The reasoning is that if the wavelength of the gravitational wave matches the atomic diameter, atomic, all material may rise and fall in unison, hindering the settling of individual atoms into more ordered arrangements. Wavelengths shorter than atomic may not create effective valleys for atoms to settle into. The optimal effect is achieved when the wavelength lambda is twice the atomic diameter of the primary material. Lambda equals 2 times the atomic. This ensures that adjacent atoms experience opposing phases of the wave, one at a peak, one at a valley, maximizing their relative motion and effectively jostling them into open spaces, much like shaking marbles on a tray to encourage settling. Given that gravitational waves propagate at the speed of light, c, the base formula for this optimal frequency is F equals c divided by 2 times atomic, where c is the speed of light and atomic is the atomic diameter of the primary element. Series 1: Conceptual Design and Theoretical Application Challenges. Exercise 1.1: Mobile Remediation Forge. Scenario: a mobile unit is needed to smelt radiologically contaminated scrap metal on site, safely removing cesium-137 and other heavy isotope particulates. Task: design a schematic for the intake and filtration ductwork of a mobile forge. Specify where you would place RAG field generators. Using the principles of centrifugal casting as your baseline, explain how a non-rotational RAG system overcomes the limitations of a mechanical cyclone separator for this task. Detail the sequences of field strengths you would use to selectively remove the heaviest and most dangerous isotopes first. Calculate the base oscillation frequency for refining the primary metal, e.g. iron, with an atomic diameter of approximately 248 picometers, using the formula F equals c divided by 2 times atomic. Exercise 1.2: Iterative RAG Technology Enhancement. Prompt: utilizing the application principles in this module, RAG forging, provide examples of how the material advancements achievable with RAG technology, e.g. ultra-pure base metals, precisely separated isotopes, could be used to improve upon the foundational RAG technology itself. For instance, consider how RAG refined materials might enable the construction of RAG system components, like field emitters or containment vessels, that can withstand or generate even higher intensity fields, or allow for more precise field control. Series 2: Empirical Protocol and Metric Development Exercises. Preamble: having conceptualized applications like the mobile remediation forge, the subsequent challenge is to develop a comprehensive experimental plan. This plan should aim to characterize the operational performance of RAG systems and validate the core RAG principles upon which their design is based. For these exercises, assume access to a functional RAG prototype equipped with tunable field strength and oscillation parameters, alongside appropriate, though necessarily advanced, sensor arrays capable of in situ and ex situ measurements. Exercise 1.1: Establishing performance metrics and experimental validation for RAG systems. 1. Defining and measuring filtration and separation efficiency. The primary function of the RAG forge is the purification of materials through the removal of contaminants. To quantify its effectiveness, specific and measurable metrics are essential. Drawing inspiration from established practices in material science and metallurgy for assessing purity and separation, a robust set of key performance indicators, KPIs, must be defined. For instance, the concentration of impurities is often measured in parts per million, ppm, or parts per billion, ppb, and the effectiveness of a separation process can be quantified using separation efficiency formulas that consider the recovery of valuable material versus the rejection of waste. Students should propose KPIs such as contaminant reduction ratio, CRR, defined as final contaminant concentration for specific target isotopes, e.g. cesium-137. This metric directly assesses the decontamination capability. Purity of reclaimed material. The target maximum allowable concentration of residual contaminants in the process primary metal, e.g. iron, expressed in ppb or ppm. Yield of valuable material. the percentage of the primary metal recovered from the initial feedstock, indicating process losses. Throughput, the mass of contaminated material processed per unit time, e.g., kilograms per hour, a critical factor for practical applicability. Energy efficiency, the electrical energy consumed by the RAG system per unit mass of material processed, kilowatt hours over kilograms, or perhaps more relevantly, per unit mass of specific contaminant removed, kilowatt hours over grams of cesium-137 removed. Task, for each proposed KPI, describe a hypothetical experimental setup detailing the specific measurement techniques to be employed. For example, to measure contaminant concentrations, techniques like inductively coupled plasma mass spectrometry, ICP-MS, or X-ray fluorescence, XRF, could be considered for their sensitivity and elemental specificity. Discuss how sample collection, both pre and post-processing, would be managed to ensure representative analysis. Furthermore, identify potential sources of experimental error, e.g., sampling bias, instrument calibration drift, matrix effects and analysis, and propose strategies to mitigate them, ensuring the accuracy and reliability of the performance assessment. The development of metrics for a revolutionary technology like RAG forging often involves adapting and extending established measurement principles from related, mature fields. Students should not aim to reinvent fundamental metrology, but rather learn to apply existing knowledge creatively to this novel context. The principles of quantifying material purity and separation efficiency are well established in conventional metallurgy and chemical processing. The intellectual challenge lies in thoughtfully selecting, adapting, and potentially combining these existing metrics to accurately reflect the unique operational characteristics and performance goals of a RAG-based system. This exercise encourages students to recognize that a key skill for engineers working at the forefront of technology is the ability to leverage and creatively adapt the vast body of existing scientific and engineering knowledge to new and unfamiliar problems. 2. Investigating oscillating field parameters, impact on refinement. The manual states that oscillating RAG fields dramatically improve refinement, provides a base formula for an optimal frequency. F equals C divided by 2 times atomic. A critical research task would be to experimentally verify this claim and explore the parameter space for optimization. Task, design a series of experiments to validate the predicted optimal oscillation frequency. For a specific primary material, e.g., iron, with an atomic diameter of approximately 248 picometers as per design exercise 1, conduct experiments by varying the oscillation frequency around the theoretically predicted value. The dependent variable would be a measure of refinement, e.g., final purity of iron, or removal efficiency of a specific contaminant. Investigate the relationship between oscillation amplitude and refinement. While frequency is addressed, the amplitude of the gravitational tides is also likely a critical parameter. Design experiments to assess how varying the amplitude of the RAG field oscillation at or near the optimal frequency affects refinement efficiency and purity. Explore complex waveforms. The manual mentions a simple AC on DC equivalent. Investigate if more complex oscillation waveforms, e.g., frequency sweeping, pulsed fields, or superpositions of multiple frequencies, could enhance the separation of a mixture of contaminants with different atomic characteristics or improve overall refinement. For these investigations, clearly define the independent variables, frequency, amplitude, waveform characteristics, and dependent variables, e.g., CRR, final purity, separation time. Specify necessary control groups or baseline measurements, e.g., processing with a static RAG field of equivalent mean strength. Detail how refinement improvement will be quantified statistically to determine significance. 3. Quantifying mass discrimination capabilities. A core principle of RAG technology is mass discrimination, which allows for precise, layered separation based on the mass of particles or isotopes. The ability to resolve and separate materials with small mass differences is a key performance characteristic. Task: propose an experimental protocol to quantify the mass discrimination resolution of a prototype RAG system. How would the minimum mass difference, delta M, between two particle types that the system can effectively separate be determined? This could be expressed as a relative resolution, M delta M. What specific metrics would define effective separation in this context? Consider, for example, the cross-contamination levels in adjacent separated layers, e.g. percentage of mass A found in the layer intended for mass B. Conduct these experiments safely and effectively. Consider using a well-characterized mixture of non-hazardous isotopes with known distinct masses, perhaps specially fabricated microparticles of identical size and shape but differing densities/masses. Outline the analytical techniques, e.g. spatially resolved mass spectrometry on solidified layers, or optimal tracking of fluorescently labeled particles if in a fluid medium, that would be used to assess the degree of separation. 4. Formulating predictive equations for particle behavior under RAG conditions. The manual draws an analogy between hypergravity filtration in RAG systems and sedimentation described by Stokes' law. However, the extreme gravitational forces and oscillating fields inherent to RAG technology likely push beyond the domain where classical Stokes' law, Fd equals 6 pi mu RV, where mu is dynamic viscosity, r is particle radius, and v is particle velocity. 4 provides accurate predictions. This section directly addresses the need to establish new or modified equations informed by existing physics. Task: begin by critically analyzing the classical Stokes' law. Discuss its underlying assumptions, e.g. rigid spherical particles, laminar flow, continuum fluid, no slip boundary conditions, constant gravitational field, and identify which of these assumptions are likely violated or require significant modification in the context of a RAG system. Consider the implications of extreme gravitational amplification and the introduction of gravitational tides via oscillating fields. Propose potential modifications or additional terms to Stokes' law that might better predict particulate settling or migration velocity within a strong, potentially oscillating RAG field. For example, would the effective viscosity of the medium change? How would the oscillating field contribute to particle motion, as an additional force term, or by modifying drag characteristics? Alternatively, sketch the foundation of an entirely new formulation if Stokes' law is deemed fundamentally inadequate. In fluid dynamics, dimensionless numbers like the Reynolds number help characterize flow regimes. Propose analogous dimensionless numbers that might be relevant for characterizing particle behavior and flow regimes within a RNG environment. These might incorporate RAG field strength, oscillation parameters, particle properties, and fluid properties. Identify which specific empirical data to be obtained from the experiments designed in parts 1, 2, and 3 of this exercise, e.g. settling rates of known particles under varying field conditions, would be essential to validate, calibrate, and refine the proposed equations or new formulations. Established physical laws, such as Stokes' law, provides invaluable starting points for understanding new phenomena. However, when technologies operate under conditions far removed from those for which these laws were originally formulated, as is the case with the extreme and dynamic gravitational fields in RAG systems, a direct application is often insufficient. The novel conditions may necessitate extensions, modifications, or even the development of entirely new theoretical frameworks. The experimental data gathered from characterizing RAG performance, e.g., actual particle settling velocities under various field strengths and oscillation frequencies, becomes crucial. This data serves not only to quantify performance, but also to feed back into the refinement of theoretical models. This iterative process, where experimental findings inform and reshape theoretical understanding, and where improved theories then guide further experimentation, is fundamental to scientific and engineering progress, especially when exploring the frontiers of new physics and its applications. This exercise aims to instill an appreciation for this dynamic interplay. And yep, this is the end of Module 1. We have another table here. Again, not going to read it. If you want to read it, just pause the video. I'm going to slowly scroll through it before we move on to Module 2. Module 2. Gravity Kiln Crystallization. Achieving Atomic Perfection. While REG forging addresses the challenge of material purity, many advanced applications demand not just purity, but also perfect atomic order. Conventional materials, even when pure, are typically polycrystalline, meaning they are composed of countless tiny crystals, grains, with random orientations. The boundaries between these grains are inherent weak points, limiting strength, conductivity, and other critical properties. This module introduces gravity kiln crystallization, a technology designed to overcome these limitations by synthesizing materials, particularly metals, with a near-perfect single crystal lattice. It leverages Class 1 radiant, Type 2 inverse gravity, RIG, and Type 3 occluded gravity, ROG, fields to construct materials with an unprecedented degree of atomic arrangement. Academic foundation. Single crystal growth and natural analogs. The immense value of materials formed as a single crystal is already a cornerstone of high-performance engineering. Single crystal nickel-based superalloys are grown using methods like the Bridgman technique for use in jet engine turbine blades. The absence of grain boundaries, the typical weak points in polycrystalline metals, gives them vastly superior mechanical strength and resistance to creep at extreme temperatures. The gravity kiln aims to perfect this concept. Alright, and before we get to meteoritics, there's quite a few things I'm not sure I've been pronouncing correctly, but there's in the next 2 sentences, there's like 4 things I'm not sure I'm going to get right, but I'll do my best. Iron nickel meteorites that have cooled over millions of years in the vacuum of space exhibit a Weidmann-Staten pattern. This pattern is the visible manifestation of enormous kamacite and tannite crystals that grew far larger than any achievable on Earth. These meteorites are a testament that, given the right conditions, slow cooling, microgravity, metals will naturally form a highly ordered crystalline state. The gravity kiln uses ROG and RIG fields to replicate these ideal million-year conditions in a controlled, accelerated process. 4 principles of gravity kiln operation. Isolation, 0G. The kiln's outer ROG field shields its interior, replicating the null gravity of deep space. Centering, microgravity. The inner RIG field gently centers the molten material, preventing contact with any surface and eliminating nucleation sites, similar to containerless processing experiments on the ISS. Induction melting and vibration. Coils melt material and introduce resonant frequencies, promote atomic alignment. Controlled core cooling and crystallization. By controlling the thermal gradient, the material solidifies from the core outward, growing into a single, highly perfect crystal, scaling the principles of the Bridgman technique to an unprecedented level of perfection. While perfect is an ideal, gravity kilns aim to drastically reduce or eliminate defects common in conventional methods, achieving unprecedented levels of crystalline purity and order. Properties of crystalline materials: maximum density and strength. As observed in single crystal applications, the elimination of grain boundaries maximizes theoretical density and strength. Superior magnetic potential. In ferromagnetic metals, e.g., iron, cobalt, nickel, magnetic strength is governed by the exchange interaction, a quantum mechanical effect that dictates the alignment of electron spins in adjacent atoms. This interaction is acutely sensitive to interatomic distance and thermal vibration. By bringing atoms into a perfect, tightly packed lattice and minimizing thermal energy, crystallization dramatically strengthens the exchange interaction, leading to a much more powerful and stable magnetic domain alignment than in any polycrystalline magnet. Foundation for advanced TMF applications. The atomically perfect single crystals produced by gravity kiln crystallization are not merely high performance materials in their own right. They represent the essential building blocks for the most advanced applications of transphasic material fusion, Module 3. The flawless atomic structure and maximized intrinsic properties of these crystals are prerequisites for achieving the theoretical performance of TMF-derived systems, such as hyper-efficient generators or the forever battery, where any imperfection at the atomic scale could compromise the unique interpenetrating lattice structures or the perpetual internal stresses TMF aims to create. Series 1: Conceptual Designs and Theoretical Application Challenges. Exercise 2.1: Enhancing Stellarator Performance with Advanced Materials. The Wendelstein 7X Stellarator is a leading experimental fusion device. Its performance is intrinsically linked to the quality and properties of the material used in its construction, particularly for its complex superconducting magnet system, vacuum vessel, and plasma-facing components. Task: Drawing upon the principles of radiant augmented gravity, RAG forging Module 1, and gravity kiln crystallization, Module 2, identify and describe multiple potential material-based enhancements to the Wendelstein 7X Stellarator. For each proposed enhancement, specify the Stellarator components you would target, e.g. superconducting coils, coil support structures, vacuum vessel, diverter plates, diagnostic windows. 2. Explain which technology, RAG, gravity kiln, or a combination, you would apply to the materials for that component. 3. Describe the specific material improvements you anticipate, e.g. increased purity, perfect crystal structure, enhanced magnetic properties, superior mechanical strength, improved thermal conductivity, reduced outgassing. 4. Theorize how these material improvements would translate into enhanced performance or operational capabilities for the Wendelstein 7X, e.g. stronger magnetic fields, longer plasma pulses, higher plasma temperatures, improved confinement, reduced maintenance. 5. Aim to identify at least 3 distinct applications of these technologies to different components or material aspects of the Stellarator. Exercise 2.2: Iterative Gravity Kiln and RAG Technology Enhancement. Prompt: Utilizing the application principles in this module, gravity kiln crystallization, and the preceding module, RAG forging, provide examples of how the material advancements achievable, e.g. ultra-pure feedstocks from RAG, perfect single crystals from gravity kilns, can be used to improve upon these foundational technologies themselves. Specifically, discuss how gravity kiln produced crystalline materials with their superior strength, thermal stability, and potentially unique electromagnetic properties could be used to construct more durable, efficient, or powerful RAG forged components. e.g., field emitters capable of sustaining higher energy densities, or containment vessels with enhanced structural integrity under extreme gravitational loads. Series 2: Empirical Protocol and Metric Development Exercises. Preamble: the gravity kiln technology promises materials with a perfect crystal lattice, and, as a consequence, unparalleled physical and mechanical properties. The subsequent research challenge is to devise a rigorous experimental program. This program must aim to quantitatively assess the actual degree of perfection achieved in materials produced by a prototype gravity kiln, and to experimentally validate their theoretically predicted enhanced characteristics. Assume access to a variety of crystalline samples produced by the kiln under different processing conditions, as well as a comprehensive suite of advanced material characterization equipment. Exercise 2.1: Characterizing crystalline perfection and validating enhanced material properties. 1. Developing metrics for crystal lattice perfection. The claim of a perfect crystal lattice and the elimination of grain boundaries represents an idealized state. In reality, all crystalline materials contain some level of defects. Therefore, quantifying the degree of perfection is paramount. This requires a multimodal approach, as no single measurement can holistically define crystalline perfection. Task: propose a suite of metrics to assess the degree of crystalline perfection in samples produced by the gravity kiln. For each metric, identify appropriate characterization techniques, discuss necessary sample preparation, and describe the expected signatures or quantitative values that would differentiate a nearly perfect crystal from a conventionally produced high-quality crystal or a less perfect kiln-grown sample. Consider the following. Grain boundary density. How would the presence or absence of grain boundaries be quantified? Techniques like electron backscatter, diffraction, EBSD, are powerful for mapping crystal orientations and identifying grain boundaries. What would be an acceptable threshold, e.g., number of boundaries per unit area or volume, for a material to be designated single crystal for practical purposes? Dislocation density. Dislocations are line defects that significantly influence mechanical properties. How could dislocations be visualized and their density, e.g., lines per centimeter squared, measured? Transmission electron microscopy, TEM, and STEM are suitable for this. Lattice parameter uniformity. A perfect crystal should have highly consistent lattice parameters throughout its volume. How would variations in lattice parameters be measured across a large sample? High-resolution X-ray diffraction, XRD techniques, can provide precise lattice parameter measurements. Mosaicity. Mosaicity refers to the misorientation of small crystalline blocks within a larger, single crystal, and is a key indicator of crystal perfection, often assessed using X-ray diffraction rocking curve analysis. How would this be quantified, e.g., full width at half maximum of rocking curve peaks? The pursuit of a perfect crystal lattice pushes the boundaries of material synthesis. Consequently, the methods to verify such perfection must also be at the cutting edge. This exercise compels students to think critically about how existing advanced characterization tools, typically used for materials with known defect types and densities, can be applied to assess a potentially unprecedented level of structural order. It involves understanding the detection limits of these techniques and how to interpret their outputs when searching for vanishingly small imperfections. 2. Experimental verification of superior mechanical and physical properties. The manual asserts that gravity-killed materials will possess maximum density and strength. These claims require rigorous experimental verification. Task: design experiments to Compare the key mechanical properties of gravity kiln produced single crystals against their highest quality conventionally produced polycrystalline counterparts, and, where available, against theoretically predicted maximums for the material. Properties of interest include tensile strength, yield strength, ductility, and creep resistance, particularly at the extreme temperatures relevant to applications like jet engine turbine blades. Precisely measure the density of the crystalline samples. How would maximum theoretical density be confirmed, accounting for minute variations due to isotopic composition or point defects? Explore the applicability of various non destructive testing (NDT) methods for assessing the internal integrity and uniformity of large crystalline components. Could advanced ultrasonic testing techniques, e.g., detecting subtle internal flaws or variations in acoustic impedance, or perhaps novel NDT approaches, be adapted for quality assurance of these unique materials? Other NDT methods like radiographic testing, magnetic particle testing for ferromagnetic materials, or eddy current testing might also be considered for specific defect types or material characteristics. 3. Quantifying enhanced magnetic potential in crystalline ferromagnets. For ferromagnetic materials like crystalline cobalt iron, proposed for the synthetic magnetar fusion reactor coils, the manual predicts a dramatic strengthening of the exchange interaction, leading to much more powerful and stable magnetic domain alignment. The exchange interaction is a quantum mechanical effect critical for ferromagnetism, sensitive to interatomic distance and lattice perfection. Task: for a ferromagnetic material produced by the gravity kiln, propose a series of experiments to quantify the enhancement in key magnetic properties. These include saturation magnetization, MS, coercivity, HC, remanence, BR, and Curie temperature, TC. How would these values compare to the best existing magnets? How could the strength of the exchange interaction or the perfection of magnetic domain alignment be experimentally probed or inferred? Consider techniques such as neutron diffraction, which can map magnetic structures, magnetic force microscopy, MFM, for imaging domain structures at the nanoscale, or SQUID, superconducting quantum interference device, magnetometry for highly sensitive magnetic measurements. Develop a testing protocol to assess the stability of these enhanced magnetic properties under various operational stresses, such as temperature cycling, exposure to external demagnetizing fields, and mechanical vibration. 4. Assessing gravity kiln process control effectiveness, ROG/RAG fields. The efficacy of the gravity kiln relies heavily on the precise control of the occluded gravity ROG fields for isolation and inverse gravity RIG fields for centering the molten material. The stability and uniformity of these fields are critical to achieving the desired crystalline perfection. Task: develop a research plan to determine the sensitivity of final crystal quality using metrics from Part 1, such as dislocation density or mosaicity, to controlled variations in ROG and RIG field strength, uniformity, and stability during the growth process. What in situ monitoring techniques, even if currently hypothetical, could provide real time feedback on the molten material's position, shape, and the ambient gravitational environment within the kiln during operation? How would logged ROG/IRG field parameters, e.g., field strength fluctuations, gradient variations, during a crystal growth run be correlated with post growth defect mapping and overall crystal quality metrics? This involves establishing a clear link between process parameters and material outcomes. 5. Designing experiments for mineral fusion and energy harvesting metrics. Magnetar scenario. The original design exercise for Module 2.1 included a highly speculative scenario, drastically increasing the RIG field in a stellarator to enable mineral fusion, turning the material into a magnetar whose emissions, mineral slag, can be harvested for energy. While deeply theoretical, defining potential metrics and measurement approaches is a valuable exercise in engineering foresight. Task: focusing on the mineral fusion and energy harvesting aspects of the original synthetic magnetar concept. What specific measurable outcomes would define successful mineral fusion? This might include the elemental and isotopic composition of the resulting mineral slag. Is it different from the input minerals in a way that indicates nuclear transmutation or novel compound formation? The quantity of energy released per unit mass of input mineral, and the conditions, e.g., RIG field strength, temperature, pressure, under which this fusion occurs. Propose methods to characterize the mineral slag emissions. What type of energy, e.g., electromagnetic radiation across various spectra, kinetic energy of particles, or particles would theoretically be expected from such a process? How could these emissions be detected, measured, and their energy content quantified to assess the potential for energy harvesting? How would the overall efficiency of the speculative energy conversion process be defined and calculated? E.g., energy harvested, energy to dry process, slash energy content of input minerals. Even for technologies that exist only at the conceptual or highly speculative frontier, the discipline of attempting to define success metrics and outline hypothetical, yet physically plausible measurement strategies is a critical engineering skill. It forces rigorous, structured thinking about the desired outcomes, the phenomena that would need to be observed and quantified, the potential challenges in doing so. This process can help refine the concept itself, identify key uncertainties, and guide future theoretical or early stage experimental efforts. It encourages students to approach even the most audacious ideas with a mindset geared towards eventual empirical scrutiny. And this is the table for Module 2. Again, same rule. If you want to read it, just pause the video as I scroll through it. But yeah, screw these tables. How did I get this? Way funnier if I don't tell you. What is this? Also refer to what I just said. It's way funnier if you don't know. But yeah, so just take it for what it is. And we have two more things like this we're going to look at on the channel. Two more documents from a certain US government program, which is in a questionable state of development right now. But yeah, I'm going to keep a few more things coming, and we'll see how things develop down the road. So thanks for watching, guys. Hope you enjoyed. Let me know what you think in the comments. And yeah, I'll see you later.